Alright, so today we're going to take a look at some applications of rational equations, and we're also going to get out our graphing calculator and use that to help answer some of these questions. So the first thing we've got here is a popular amusement park wants to add new rides and asks various contractors to submit ideas. Suppose one ride engineer offers plans for a ride that begins with a near vertical drop into a dark tunnel at ground level, quickly turns and becomes more horizontal, pops out of the tunnel's end, then coasts up to the exit platform, braking 20 meters from the release point. All right, so that's the scenario, and it says then that the height of the rider above ground is modeled by the function h of x, and you can see it here. It doesn't look too pretty, does it? Where h of x is the height, so we know that h of x equals height, so we definitely want to keep that in mind. H of x equals height, and in meters. Alright, so that's an important thing. At a horizontal distance of x meters, so x equals horizontal distance. Alright, in meters. So it says graph the function for x in the set of numbers -1 to 20. Alright, so we're going to get out our graphing calculator and we're going to go ahead and graph this. So in your graphing calculator, you're going to want to hit the y equals button. So if you open up and you're in this menu here, you're going to want to hit the y equals button. In y1, you're going to hit the alpha key, and then you're going to hit the y equals button again, and it's going to bring up this fraction, this other menu. You're going to hit number 1, and it's going to give you a fraction here. So we're going to type in the equation 39 x to the second power minus 507x plus 468 all over 3x squared plus 23x plus 20. Now you'll notice it said in the lesson that the window for this was supposed to be x from -1 to 20. So the next thing we want to do is we want to go to this little button at the top that says window, and we're going to hit that, and we're going to change this from -10. We can just clear that out of there, and we're going to do -1, and the maximum is going to be 20. Alright, we're going to leave the x scale alone. The y min, it does say it goes under the ground. The y max, though, we don't know how high we're starting out here, so at this point I'm just going to hit graph and see where we're at. If we need to adjust the y max, we'll do that. So if we hit graph, alright, so here's my graph, and alright, I can see where it goes down under the ground, right at, looks like right around x equals 1, coming out of the ground over here somewhere. I'm sure it said that in the story, but the y-axis definitely looks a little long. I'm not getting much of a view of my graph down at the bottom here. So let's go back to the window and adjust that y-axis. Okay. So even though the graph goes all the way up, I'm not quite sure how high we actually need to go. So I'm going to adjust it to more like, I'm just going to try 30 and see what happens here. I'll hit graph again. Okay. Alright, I'm going to stop for a minute and double check my equation here. Okay, so as you can see, I was missing the 0 on the 20 in the denominator here, so hopefully you caught that. It should be 23x plus 20 here. So I'm going to go back to my graph, take another look here. Alright, so definitely looks like my graph is now crossing the y-axis somewhere up there towards the top. So it's looking better than it did. Alright, so question number 1 said to graph, or part A said to graph the function. Looks like we got a pretty good graph going here. We're going to leave that alone. Part B said how high is the release point? The release point is the point where it touches the y-axis here. Now there's two ways to do that, okay? So I'm gonna go back to here for a minute. It says, how high is the release point? Now you gotta think about this. The release point is when x equals 0. When x equals 0. Before I've gone any horizontal distance, I haven't been anywhere. I should be at the top of the ride when x is equal to 0. Well, one of the ways I can do this is simply plug it into the equation, right? So h of 0, now look at the equation. 39x squared times 0 is going to be 0. 507 times 0 is going to be 0. All we're left with is 468 in the numerator. And the denominator is 3x 3 times 0, which is going to be 0. 23 times 0, which is 0, plus 20. So we end up with 468 over 20. All right, and if you do a little bit of math, you take out your calculator and divide those out. It turns out that this is 23.4, and we're talking about when x is 0, what is h? So this is 23.4 meters high. So before the ride's released, you're up in the air about 23.4 meters. Now if you go back to your graphing calculator, we can actually have the calculator do that. So one of the first things we want to do here is we want to check out our table. All right, we're gonna look at a table here. So the first thing we want to do is we want to hit second, and then before we hit table at the end, I want you to hit table set. Okay, the key right above window. So you're gonna hit that window key, and it's gonna bring you to this menu. So we're gonna start the table at 0. If it's not 0, go ahead and punch in 0. We're gonna scroll down. Table. This is the change in the table, so you can just leave that by 1. So that's fine. And then the thing you really want to make sure is highlighted here is the word ask on independent. So you just want to scroll down, hit enter on there, make sure that that's highlighted. And then let's go to the second key again. Hit the graph key again, because that's going to bring up the table. All right, so here I've got a table, and I want to know, hey, look at that. When x is 0, I get 117 over 5. Now, is 117 over 5 the same as 23.4? Let's find out. Okay, so what the table will do for me is it will give me values along the way. I can punch in anything I want. If I want to know where I'm at 1 second or 2 seconds or 3 seconds, okay, so I'm actually going to go ahead and just delete the rest of these guys so that we're only looking at values that are applicable to our graph. So let's quit out of here. Let's hit the second key and quit. And let's just do 117 divided by 5. Hey, look at that, 23.4 meters. That's exactly what we got. All right? So that's question B right there. Question C says, how long is the tunnel from entrance to exit? All right, so if I go back to my graph again, from entrance, you can see, I'll hit the graph again. You can see the entrance is somewhere right around here, around x equals 1. Okay, now we're going to find out exactly where, and it looks like it exits somewhere over here. What are we looking at? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, somewhere around 12. Now those could be exact numbers, but there's a couple of different ways to figure out, and that's what we want to do here. All right, so we want to figure out the distance from where the ride goes in to where it comes out. So let's go back to our second key, hit the second key, hit the trace key, because right above that it says calculate. What we're going to do is we're going to calculate the 0. We're going to calculate the x-intercept. So you're going to hit number 2, and you can see the cursor blinking there. So let's go ahead and calculate the one that looks like it's around 12 there. So it's going to scroll out. You'll notice this at the bottom left screen it says left bound. What they want you to do is they want you to give a guess as to where it's crossing the x-axis on the left side of where you think it's crossing. So you can see I'm at 11.25. I'm going to say okay, close enough, and I'm going to hit enter. Then it's going to say give me a right bound guess. So I'm going to go to the right side. You can see I'm up at 12.5. I'm definitely above the y-axis because it says y equals 0.3. So I'll hit enter. It says give me a guess. I think you can just hit enter again. Hey, look at that. It comes out at exactly 12 meters from the horizontal starting point. All right. So 12 meters out, so we're exact there. Let's go back and calculate the first one. Let's go second, trace again. We're going to calculate the first 0. So now we're going to go all the way back over to the one that's over by 1 somewhere, it looks like. All right, so we're going to scroll back over here. Takes a while to do this sometimes. So again, we need a left bound, so I need to be above the x-axis, which I am because my y value is 0.9. So I'll hit enter, and I need a guess to the left of 1, now below the x-axis. So I hit enter again. It asks me to take a guess, so I'm just going to hit enter, and guess what? Hey, look at that. X is equal to 1. So the distance of the tunnel here, how long is the tunnel from entrance? Entrance is x equals 1. Exit is x equals 12. So the tunnel is 11 meters long. All right? What is the height of the exit platform? Okay, so you can see that as it says that the ride breaks right up here in the scenario. It breaks 20 meters from the release point. So if we go back to the calculator, basically, if you look at the right side of my graph over here, I've got 20 meters. Horizontal distance, I need to know how high that point is. Well, guess what? I'm going to go back to my table. So I'm going to hit second and table, and I want to know how high that ramp is when I'm 20 meters away from the start point. So if I punch in 20 and I hit enter, I get 247 over 70. All right? Now there is a way to do this in decimal. We'll talk about that later, but 247 over 70. So I'll hit second and quit, and I'll just punch in 247 divided by 70, and it turns out that I am 3.5 meters above the ground when I'm on the exit ramp. All right? So what is the height of the exit platform? Approximately 3.5 meters high. All right? Because both X and H are in meters, we want to make sure we're specifying how long versus how high things are. All right? So that one wasn't too bad, was it? It was kind of fun. We can design roller coasters here one day, maybe. All right? It's probably a little more involved than that. All right, here we go. Population density. All right? Number 3, not quite sure what happened to number 2 in here. Not going to worry about it. Number 3 says the population density of urban areas, not sure what that plus sign is doing in there, don't worry about that. I should say urban areas in people per square mile. Okay, so this is people per square mile, can be modeled by the formula shown where A and B are constants related to the overall population and sprawl of the area under study. And D of X is the population density in hundreds, X miles from the center of downtown. Okay, so X represents the number of miles from the center of downtown. D of X is your population density in hundreds. And A and B are constants that are based on the overall population. All right, so we're going to graph the function for A equals 63 and B equals 20 over the interval 0 to 50, and then we're going to graph and answer the following questions. So we need to go back to our calculator. We're just going to go ahead and clear off this screen. We're going to go to our y equals, and we're just going to hit clear, and then we're going to graph the new function. So we go to the alpha key, the y equals key, that pulls up your menu. Hit number 1 for fraction, and let's type in what we've got here. So we have d of x, which is our function. We need a equal to 63, so this should be 63x, all right, in the numerator. And our denominator is x squared plus b. So x squared plus, and they told us that b was equal to 20. right? So there we go. And let's go to our window and adjust that, because they did tell us to graph over a 0 to 50 window. So we're going to go ahead and clear this out and type in 0. We're going to go all the way out to 50 this time. So 50. And now you can notice by my little, normally you wouldn't see this, but you can notice I've got a lot of room above this graph on the y-axis here. So normally you just have to take a guess at your y max, okay? And it doesn't look like I'm going much below at all, so I'm going to adjust those numbers as well. So I'm going to adjust my y min maybe to -2. Okay, we'll go ahead and take off the 20 there, make that -2. And the y max, boy, it's at 30 now. I'm going to try 10. All right. And I bet you if I scroll down, let's see what we get there. Let's go ahead and graph that. Okay, so that gives me a better idea of what I'm looking at here too. And so there's my graph. All right. So if you look at the first question, it says, what is the significance of the horizontal asymptote? What does it mean in this context? Now, if you look at your equation, right now my equation is d of x equals 63x over x squared plus u is 20. So if I just gave you that equation and said, hey, what's the horizontal asymptote? You would hopefully tell me that it's 0, okay? Because the degree of the numerator is less than the degree of the denominator. So right away I know that this value here, my horizontal asymptote, should be y equals 0. Now if you look at your graph looks like it's coming down, and we're not only out to 50, but eventually it's going to get down closer and closer to the y-axis, okay? Now, you got to keep in mind that, you know, as numbers get bigger and bigger and bigger, this graph is always going to hover above the y-axis, okay? It's never going to reach 0. It's always going to hover above. And so when you look at this graph, what the y values are telling you is your population density. So you can see that your population density grows, and somewhere around 5 or 6 here we reach the peak of the population density when x is 5 or 6. So that would indicate about 5 to 6 miles from the center of downtown your density is at the highest. And then as x increases, you're getting further away from the center of town, which means your population density is going to decrease. But if I continue to hover above the x-axis, that means that my population density will never actually reach 0. And if you think about it, no matter how far you drive away from the center of a town, there's always going to be somebody living somewhere, whether it's close to town or far away from town. Okay? So that's kind of what that means in context. It means that, you know, the horizontal asymptote is y asymptote. There we go. Horizontal asymptote would indicate that the population density would never reach 0. And again, that's based on the fact that no matter how far you go out from downtown, there's always going to be people living somewhere in the area. Okay? Letter B says, how far from downtown does the population density fall below 525 people per square mile? Now, when we say 525 people per square mile, you got to remember the population density is in hundreds. So all these numbers we're looking at here, when you look at your graph, you know, we're only graphed up to a y value of, what does it look like? 1, 2, 3, 4, 5, 6, 7. But what that indicates is 700 people. The population density is 700 people. So again, we're in hundreds here. So if we go back here, how far does the population downtown, how far from downtown does the population density fall below 525 people per square mile? What we're asking here is basically, you know, when does d of x, or when is d of x, what I'm going to look at is when does d of x equal 525? Now I know it talks about being less than that, but if I know where d of x is equal to 525, then I can say everything below that, you know, fits my question here. So when does d of x equal 525? Well, let's just graph a horizontal line and see what that looks like. So let's go back here. We're going to go to y equals. Now you got to remember this is in hundreds, so we actually need to take our 525 and divide it by 100 so it fits on our graph. So we're actually going to graph the line d of x, or you can just think about it as y equals 5.25. All right, so here we go. We'll go to our y window, we'll go down to number 2, we'll graph 5.25, and we'll go ahead and hit the graph button again. It's going to add this red line. What I need to do is I need to figure out where those points are, where my graph is below the red line. Okay, so I want to know how far from downtown does the population density fall below 525 people per square mile. Now, the first dot is, if you look at your graph here, hang on, give me 1 second here. Okay, I just want to make sure my graph is right here, but okay, so if you look at the point here at 0, 0, all right, that means that I am 0 miles from downtown. And as the x values increase, I'm getting further and further away from downtown. So as the blue graph increases, my population density increases. So in the first section of blue, I'm always below a population density of 525 people per square mile. As I reach the red line the first time, I go above a population density of 525, and then I come back down the right side, and then it falls below further out to the right side. So we need to find out what the value of x is right there. That's going to tell us how many miles from downtown we are as the population falls below 525 people. So here's how we do that. We hit the second button on our calculator. We hit the trace button because right above it, it says calculate. This time, instead of calculating number 2, a 0, an x-intercept, we want to calculate number 5, an intersection. So we're going to calculate the intersection. So you'll notice it says first curve. So I'm just going to get my cursor nice and close to where they intersect on the first curve. So I'm going to go right about there, and I'm going to hit enter. And then it says second curve, and you'll notice the cursor is already pretty close, so I'm just going to hit enter. And then for some reason it asks for a guess, so we'll hit enter again. And so the intersection is at x equals 10. All right? So what that's saying is that after I'm 10 miles away from town, I'm now below 525 people per square mile. And you want to keep in mind that at x equals 10, I'm exactly 525 people per square mile. So we would want to say after 10 miles away from downtown, okay, is it exactly 10 miles? I'm still at 525. So after 10 miles away from downtown, the population density falls below 525 people per square mile. Okay? So that's the meaning of the graph at that point. Let's take a look at the last one. We've got 2 more here. So the next one says, how far until the population density falls below 300 people? Well, if I can find it at 525, I can definitely find it at 300. So basically, again, they're saying d of x equals, where's d of x equal 300? So what we're going to do is we're going to graph the line again. Remember, our graph is not in hundreds, it's in ones, so we've got to divide by 100. So we're going to graph the line y equals 3. So here we go. We'll go back to our y equals. We'll go down to the third line. We'll graph y equals 3. Graph. And then we want to find the intersection of the blue and the black. So again, we're going to hit the second key, calculate. We're calculating an intersection, so that's number 5. And my cursor's pretty close, so I'm just going to move it as close as I think I can. I'll hit enter. It's going to jump to the other curve. And you'll notice it's blinking on the red curve now. I don't want the red curve. I want the black curve. There we go. I think it's on the black curve. And then a guess at x equals 20. All right? So the explanation here is exactly the same as above. Okay? After 20 miles away from downtown, the population density falls below 300 people per square mile. Okay? And then the last question says, use the graph and a table to determine how far from downtown the population reaches a maximum. Okay, so use the graph and a table to determine how far from downtown the population reaches a maximum. So I think we're just going to do this one with the graphing calculator, because since we got it open, you can see the maximum right up here. That's the top of the blue graph. And again, it looks like it's somewhere around 5 or 6, but we can actually get the calculator to do that work for us too. So if you hit that second key again, and then hit the trace key, right above it, it says calculate. So we've calculated zeros, we've calculated intersections. Number 4 is a maximum, so we're going to hit number 4 this time. And again, cursor's going to say, hey, give me a left bound on that maximum. So we're going to scroll over here. We're going to do a left bound on that maximum. I'm going to go to the left side of the max and hit enter. And then it's going to say, give me a right bound. So I just want to make sure I'm on the right side of the curve. Hit enter again. And you can move the cursor up if you want to give it a guess, but at x equals 4.5, you notice I'm rounding up here, y is equal to 7.0 for rounding to the nearest tenth. Okay, so I'm going to use 2 decimals, and I'll tell you why in just a second here. So I'm going to just write them down. At x equals 4.5, y is equal to 7.04. Okay, y is equal to 7.04. Now we got to think about this in terms of our graph. Our x values do represent miles away from downtown, so those guys are okay. But my y values need to be multiplied by 100. So what we're really saying is that what this implies is that d of x is equal to 704. Okay, so the maximum population at x equals 4.5 miles away from downtown, all right, away from downtown, the maximum population density is, and again, this is an approximate. There were some other decimals there, so this is an approximate, just like the x value, is approximately 704 people per square mile. Okay? So it's not just 704 people, it's 704 people per square mile. All right? Okay, we're going to stop that one there and have fun with the rest.